Hey everyone, lesson 10.6 is all about systems of equations and parallel lines. Basically what happens in a system of equations if we have parallel lines. Remember, those are lines that really never intersect. Parallel lines actually help us to determine whether a system has 0, 1, or infinitely many solutions. So taking a look here, our warm-up today is to give the slope for each of the lines below. We did this in class actually last time I saw you guys. Remember that if you are in y equals mx plus b form, the slope is m, that coefficient of x. So the first two should be extremely easy. The third one is a little bit more difficult. Please take a moment to check those out. As far as the notes go, write down as much as you would like in today's notes. There is a table summarizing the info on a later slide. That table should be in your notes for sure. You may not need to write down a whole lot of other things, but the table should be in your notes for sure. Our slope in number 1 is, of course, 3/4. For graphing purposes, we would go up 3 and to the right 3. Remember, the numerator of the slope determines the vertical movement, and the denominator determines the horizontal. We call that the rise over the run. -4, for graphing purposes, this could go down 4 and to the right 1. This one's a little trickier. When we solve for y, it comes out to be y equals 2/5 x minus 2, so our slope would be 2/5. For graphing purposes, again, rise over run, this would go up 2 and to the right 2. Solutions to linear systems. All linear systems will end up having 0 solutions, 1 solution, or infinitely many solutions. If we are going to discuss nonlinear systems in the next section, and that actually gives you a couple different options. But when we're talking about linear solutions, where there is no squared variable, we are just taking a look at our 0, 1, or 2 solutions. In the graph, we can actually see 1 solution, 0 solutions, no intersection. And A, the graph of A is a little bit tricky. In the graph of A, there's infinitely many solutions because, in fact, both equations are graphed in the exact same spot. So if you could right now, please match the system of equations to its graph based on what you see in the equation. Number 1 actually matches graph C. If we were to take a look here, the system of equations could be rewritten in a y equals format by taking a look here. If we were to write this in a y equals format, we would actually come up with the two lines being parallel because they have the same slope but different y-intercepts. Different y-intercepts in the same slope. If we actually write them both in slope-intercept form right here, we can see that. Slowly kind of working our way there, one step at a time. We find out that the first equation becomes y equals -1/4 x plus 2, and the second equation equals y equals -1/4 x minus 5. So we can actually see that in the graph. The first equation is this top line, intersects here at 2, and the slope is a -1/4. And the second equation has a y-intercept of -5, and the slope is also a -1/4. Taking a look at the second one is actually a match with graph A. In line 2, the lines are actually the same. If the second equation is multiplied by 2, it is identical to the first. If the second equation is multiplied by 2, it's actually identical to the first. Multiplying by 2 would result in 2y plus 4x equals 8. And if we rearrange the terms of the second equation in our system of equations, they are actually the exact same equation, resulting in the exact same line. So the entire line is actually the solution here. So there's an infinite number. If we were to put this in slope-intercept form, we would actually see the same exact slope, the same exact intercept, because they are the same exact line. These are what we call coincident lines. The same line, it's usually written in different forms, otherwise it would be really obvious. As we can take a look, they don't look the same when we originally look at the equation. Coincident lines have the same slope and the same y-intercept. The lines are the same, so all the solutions are the same. And finally, number 3 is actually a match with graph B. The lines are intersecting. They have different slopes, and anytime you have different slopes, that would indicate that you have intersecting lines. 1 point of intersection would mean 1 solution. So if we take a look, the first equation can be rewritten in a y equals format as y equals 1/4 x minus 7/4. The second equation can be written in a y equals format as y equals negative 1/4 x minus 1/4. So the slopes look actually similar, but they are in fact opposite to one another. These are opposite to one another. So 1/4 x, a positive 1/4 slope, and a negative 1/4 slope are opposites of one another. So these lines have different slopes and will of course intersect. Intersecting lines have different slopes and 1 point of intersection. 1 intersection point indicates 1 point where both are true. 1 solution. So as promised, this is all going to be summarized here in this table. You should be able to fill in the table boxes based on what you've seen in the notes. So you should be able to make a sketch of what 2 intersecting lines, 2 parallel lines, and what 1 line looks like. You should be able to identify how many solutions 2 intersecting lines have as a system of equations, how many solutions 2 parallel lines have as a system of equations, and how many solutions 1 line has as a system of equations. And you should be able to describe the slopes of the 2 intersecting lines, the 2 parallel lines, and the single coincidental line. Now we're going to take a look at what this looks like when we're solving systems other than using the graphing. If you're substituting using the addition or multiplication elimination methods, if you're able to find 1 solution, well then of course it has 1 solution. So this is an example using the multiplication elimination method. If I multiply the second equation by -2, I would of course come up with the following system. And if I were to add the 2 equations together, this is the elimination step, I will create a third equation with only 1 variable. By adding the 2 equations together, I do get negative 16y equals 16. Eliminate the coefficient by division, and I find out that y equals -1. And then finally, I would use y to find x. I'm going to use the second equation because there's an x in it already. There's already just a plain x term. So I would say x plus 4 times -1 equals -1. A little bit of substituting and calculating here, I find out that x equals 3. Obviously, it's a good idea to check your answers by substituting our x and y values in the first and second equation of the system of equations. We find out that this is true. I was able to find 1 solution, x equals 3, y equals -1. Therefore, there is 1 solution to this equation. I can imagine the graph of this would actually be a graph of intersecting lines. If the variable zeroes out as you are working and you have a true equation, you know that there is an infinite number of solutions. This is an example by substitution. I personally would do multiplication elimination, but want to remind you what substitution looks like. The second equation gives us the fact that y equals -2x plus 4. This can be substituted into the first equation. I can solve this equation in a few different steps. First, I would do the distributive property, giving me 4x plus -4x plus 8. I would then combine like terms where x is 0 out, and I would be left with 8 equals 8. This is an instance where I was solving. I believe I've done everything correctly, and the variable zeroed out, and I was left with a true equation. This variable totally zeroed out. I was left with a true statement that 8 equals 8. That means that there are infinitely many solutions. If I were to graph these 2 equations, I would actually come up with the same line. And finally, if I am looking to solve the equation, solve the system, and the variable zeroes out and I'm left with something that is not true, a false equation, I know that there are actually 0 solutions. So again, we're going to see the multiplication elimination method. I'm going to multiply the first equation by 2 and rearrange some terms. So the first equation is multiplied by 2. Negative 2x comes from the negative x here, plus 16 comes from the 8, equals 8y. I'm going to add the first and second equations together. Now I will add negative 8y to both sides to eliminate the variable term on the right. It actually ends up eliminating the variable term on both sides, and I come up with the statement 16 equals negative 40. Since my variable zeroed out and I came up with something that is false or untrue, I know that this is not ever going to be true and that there are actually no solutions to this. I can imagine that this system of equations would actually give me a graph of 2 parallel lines. These are the in-class examples that we will be looking at. It would probably be a good idea to at least try and get a start on these so that you have an idea of what types of questions you'd like to ask when I see you next. Thank you.